So now we're going to talk about Bayes' rule. What is Bayes' rule exactly? So Bayes' rule is trying to find the probability that we observe one random variable, like here, what's the probability that we will observe A, given that another random variable like B has occurred. So what's the probability of A given B? So what it is equal to is it's equal to the probability of B given A multiplied by the probability of A divided by the probability of B, which is also equal to the probability of A and B divided by the probability of B. So in other words, the posterior probability of A being true given that B is true is given by this likelihood, the probability of B being true given that A is true. So whenever you see in probability problems, whenever you see this part here, this part is just saying given. That's what this part is representing, given. So it's always the probability of, this part right before the line, given that this one was observed. So this is the probability of A being true, given that B is true. So whatever's on the right is sort of right, and it's sort of what happened first. And then this is the probability of us observing that A, given that this has happened. So this flipped around, you'll see that this and this likelihood, they're flipped around in a way. So this is the probability of B being true, given that A is true. So one way of seeing it is the probability of B being true. Oh, okay, that's probably not the neatest color. So let me just underline it. So this is the probability. Oh, I can't do that either. Okay, let me try it again. Of B being true. So, but here it's flipped around where B is actually true. In this one, B is true. But here it's the probability of B is true, given that A is true. So this one is given that A is true, and this one is the probability that A is true. And you can see that they're like sort of flipped around in a way. So what this is this is the likelihood, and then this is the prior. This is the probability that A is being true. This is the knowledge. And then this is the marginalization, the probability that B is true. So if this confuses you, this over here is just the same thing as this whole expression here. This cute little expression here is just the same thing as the probability of A and B. That's what it is representing. And whenever you're saying the probability of A given B, the denominator, you can sort of think of like this A given B in a way. You can think of it as like this A and then this B. You can think of this part here, this given part, as sort of like, you could think of it as sort of being like becoming the new denominator. So like B gets put on the denominator in a way. You can think of it like the slice is like putting B on the denominator. I look like I was doing like a Jedi Star Wars move. I love Star Wars, by the way. So this is just the same thing as the probability of A and B divided by the probability of B. So when B happens, what's the probability that A will happen? So if you have like two different outcomes here, if this is like A and this part here is B, so what this is trying to say is given that B has occurred. So now that B happened, what we will see here is that, oh no, that's the wrong color. So so what we'll see here is that B has occurred now. Okay, so B has occurred. So what is the probability that A will occur? So this is the whole like sample space, this is the sample space. You can have A, you can have B, or you can have neither. So I just drew that rectangle as a sample space. So if you now know that B has occurred, what's the probability that A will occur? So what you're going to do is you're going to essentially have in the denominator the probability that B has occurred. Then what you want to see now is that this is a new sample space. We've reduced it from that whole rectangle down to that circle of B. So now from B, what is the probability that A is true? So we want to find this overlap now. So that's how we find A and B being true. That's what we're trying to find, this part here. So ultimately, this part is how, now that B is true, that is how A can take place. So if we are now restricted to this blue set here, the only way that A can take place is if A falls in the intersection between A and B here. If it's in the common part between the Venn diagrams, that's the only way that A can happen. So that's why we look at A and B, and that's our numerator. And then we divide it by the probability of B happening in the first place. So that's how Bayes' rule is working. And if you decide, and this is the marginalization, this is shown here as well. Probability of B being true, whatever you're conditioning it on. This is a conditional probability. PA given B is a conditional probability. It is a conditional. It's a conditional probability. It's you're conditioning it on the fact out of all this whole sample space that sums up to 1. So this other shaded, other part of this rectangle is the part where A and B are not true. A or B are not true, so it's neither A nor B is true. But now if we're just doing the probability of A given B, so we are conditioning our sample space to just B being true. And now we're seeing if B is true, if we're in this blue circle, what is the probability that A will be true? And that's why we look here at the overlap between them. That's also, just to keep the color constant, that's also what this purple is trying to do. This purple is just measuring the probability of A and B. Meanwhile, this circle here is only true, for the probability of B. So this is just what Bayes' rule is, and we're just going to use that to better understand the concepts. So here I just want to give you an example of Bayes' theorem here. So again, so this thing means and I just sort of want to focus on mainly this application here, where you have P of A given B, for instance, and this part here, we're using the and part of it. So the idea is that you want to basically see the known information. So let's say that we know that probability of B is 41%, so that's like 28% plus 13%. The probability of C is 27%, so that is 13% here plus 14% here. And the probability of B and C, so a way I think about it is that, this, for and is sort of like, looks like an and. It looks like an A. That's how I sort of remember that this means and. So the probability of B and C is 13. So the 13 we will do is we'll just put this 13 like smack in the middle here. We'll just put the 13 right here. That's where we'll put the 13%. And then we can see probability of B and not C. So that 28% comes from 41%. Minus this 13% that is in between. So that just tells us that the part of B that's true and not C, where C is false, this part here, that is 28% here. That is what this 28% maps to. And similarly, the part of C that's true where B is not true, that is just, the 27% minus the 13% overlap here. So this 27% of C minus slicing off the 13% because that's when B is also true. So this is the probability that C is true but B is not true. That's 27% minus 13%, so it's 14% here. And lastly, if we're looking at the probability of not B and not C, then that's just 45%. So we look at everything here, and this all sums up to 55%. 55% is this thing here. That's what it is. So that's what the 55% is. So basically, the probability of not B and not C is 45%, that both of them are not true. That's what this is. And then you'll see that if you just add this together, probability of B and not C, if you add this part up here, the 28% plus the probability that C is true and B is not true, the 14% here, this intersection here, this 13% of probability of B and C, plus the probability of not B and not C, that blue part that was given by this. You should see that if you add all of them together, effectively you get this rectangle that is 100%. So these are all the outcomes. Either you can have B being true, only B true, and only C being true, or B and C being true, or none of them being true. So you have those 4 outcomes here that we're just summing across. So they're 100%. And now I just want to show you, now that we verified that it all adds up to 100%, so we're happy. I'll just draw my little star here. We can now use Bayes' theorem this way. So the probability of B given A, so probability of B given that C is true. That's what this is saying. What is the probability of B given that C is true? Given that C is true. That is given by the probability of B and C divided by the probability of C. So then this will be just, so we look at the probability of B and C. So this is this 13% here divided by the probability of C, which is 27%. 13 plus 14, which we see here is 27%. So basically, we are seeing now, the way that it works is we're looking at C. And we're saying, okay, well, there's this 13% overlap where B could be true. And that's what we're focusing on. We're focusing on the 13%. That's what we're focusing on. Oh, this should have been in orange. We're focused on that 13% out of the probability that C is true here. That's what we're seeing. So it's 13 out of 27. So that's the probability that B is true given that C is true. So it almost seems around 50%, which is, kind of higher than. So let me see. What is 13 divided by 27? That is 48%. Approximately 48%. So you can see that the probability of B given C is slightly higher than the probability of B by itself, which was 41%. So it gets boosted up a bit. And another way we could have also gotten the same result is we could have just, for the numerator, a probability of B and C, that is 13%. That's just the same as sort of looking at the probability of. So this thing, we could have also calculated this by just looking at the probability of C given B times the probability of B. And the probability of C given B. So to calculate the probability of C given B, what this is equal to, this is just equal to the probability of B and C divided by the probability of B. So what happens that you're going to see is that, like, if we have, this is essentially what this is. So if we try multiplying them all together, this part will just cross out with this part. And then we're just left with the probability of B and C, which is exactly what this is on the top. So it's equivalent either way that you do it. It's exactly equivalent. So now you can see that the probability of B given C gosh. probability of B given C, that's what this is just around 48%, which is boosted up over 41%. So this is just an example of Bayes' theorem. So this is the conditional probability of B given C, which is different from the probability of B outright, you know? So now I'm just going to show you an example with my cute little cat, you know, Yangshi. So we're just going to see that there. So I hope that this example sort of grilled it in for you guys. So for me, I'm a visual learner, so this would help me out as well. So again, you can see that whether you use this formula or you use this for the numerator, it's exactly the same thing. That's what A and B are. So when you get a Venn diagram like this, it's much easier for you to just skip out and having to do this step. So in this example here, I have cute little Yangshi. Hi, little guy. And I want to see an example of the application of Bayes' theorem. So now our little guy is very sleepy and tired, but there are two options for him. He can be happy, you happy, or he can be sad in this case. So there's A, that when A is true, then he's happy. But when A is not the case, when it's not A, then A is false, so the cat is not happy. So he is sad here. So this guy is sad in this case. And B is if he is fed. Are you fed? Are you hungry? And then that's when B is true, then he is fed. But when B is not the case, then he is not fed and he is hungry. He's hangry instead. So what we want to see based on this idea is what is the probability that A is true given that B is true. So what is the probability that this cat is happy given that the cat is fed? So we were just talking about Bayes' rule right now. Are you happy? He's not happy right now. But based on Bayes' rule, what we will observe is that the probability of A given B is the probability that he's happy. So we're focusing on A being true and B being true. So if A is true, if he is happy, right, and B is true, then he is also fed. So what's the probability that he's happy given that he's fed? You happy? You happy? I don't think he's very happy. You want to go? He's very sleepy at the moment. So basically what we're going to look at here is the probability. This is the posterior and we have a prior. The prior here is, okay, you want to go, sweetie? You can go. If you want to go, you can go. Okay, you can go if you want to go. Okay, he wants to go back to sleep. So basically, so yeah, I just had a cute little dessert. So what we want to see is the probability that A is true. This is the knowledge. So we have some idea of how likely the cat is to be happy. So I've observed Yangshi over these days, so I have some idea of how happy he typically is, right? And I also have an idea, you know, that he could be hungry as well, and if he's not fed, maybe he could be unhappy. So I just want to see, will he be happier if he's fed, right? I'm not sure, right? I have to put it together. I have some idea, some prior knowledge. That's what P of A is, the prior knowledge that we may have, and it's very domain specific. In some cases, we may know what this probability is. We know the probability that Yangshi, the cat, is happy. We know this. And then we also know the probability that I feed him, right? So of course, if he's happier, then there's oxytocin that's secreted. He lets me pet him and love him, and then I'm just very, very excited and happy, and I want to feed him more, and so on. I do feed him regularly, but if he's happy, then maybe I would be, you know, feeding him more in that case, right? The probability of that's what B given A is, the probability that the cat is fed given that the cat is happy. So I would need to know that. And I would also need to have some idea of what is the probability that he is happy and divided by the probability that he's fed. And again, this is the prior information, so we may know this information off the bat, but if not, sometimes we can just be given the probability that the cat is happy and the cat is fed as well. That's what A and B is, the probability that he's happy and fed. And these are the different outcomes. So green is A over here, so this is A. And then in red is B, is basically the cat is fed. And we're focused on A being true and B being true. And this gray is all the sample space of events. So for B, basically the cat is fed here. So you can see the cat's already ready to eat. And then in A, the cat's happy and loving and so happy, filled with love. And this is A and B. So the cat is fed and happy. This is the cat being fed, this is the cat being happy, and this is the cat being fed and happy. And this thing corresponds to what this gray thing is. That corresponds to this gray area here where basically the cat is unhappy and starving. So what we want to do then is we want to figure out what this is. So if you have this information for the numerator, you can calculate it this way. Otherwise, you can just find this probability. So it just comes down to focusing on the fact that, you know, the red thing is true. Oh, eeks. That we're in this part here. Sorry, my drawing isn't that great, but we're in the red part here. This is where the red part continues. And this blue again was the overlap between the A and the B. So sorry I didn't show properly, but this is the overlap. So we're focused on B being true here, on the cat being fed, and we want to find the probability that the cat is happy. So that's sort of where we intersect this with A. Oh, sorry, my drawing is off. But the way that A can be true, if B is true, is this part here where the cat is happy and fed. And then we just divided by the probability that the cat is fed. So that's all that we're doing here. So we can look at the probability that the cat is fed, given that the cat is happy. So again, that might be like slightly a good probability to measure, because if the cat's happy, maybe I want to feed the cat more. Or it could be the other way around, if the cat's very angry, and unfortunately I do make the cat a little bit angry by smothering him. I'm sorry, little guy. But maybe if the cat's angry, I feed the cat more because I want to make up for it. So it really depends. So that sort of comes down to my cat and, you know, those things. But the probability the cat's fed, given that the cat is happy, multiplied by the probability the cat is happy. And this is the prior here. This is the prior. So I would start off kind of knowing what this probability is that the cat is happy. And then the marginalization is the probability that the cat is fed. And that's also the same. So I can use this part here, kind of corresponds to this part here. Ah, gosh. And then this part here sort of corresponds to this part here. So, or I could also look equivalently at the probability that the cat is fed and the cat is happy, which is what this part is here, this blue part here. Oh, sorry, this blue part maps to the numerator. The probability the cat is fed and the cat is happy, divided by the probability that the cat is fed. This is the same thing. Denominator is the same here. It's just that the numerator, that this expression is actually the same as this expression. So the probability of A and B is equal to the probability of B given A times the probability of A. So actually, just the rules of conditional probability would say that the probability of well, this is equal to the probability of B given A times the probability of A, or it's also equal to the probability of A given B. Oh gosh. Multiplied by the probability of B. So the way that you can think of that part is that, hey, this is just basically, you would see it if you just see this over here and just this part here, that basically if you sort of black this part out for now, let's just black it out and not focus on this part, let's just black this part out here. Then what you'd see is that probability of A given B is equal to probability of A and B divided by probability of B. So if you multiply both sides by probability of B, you have probability of A and B equals this equation here, probability of A given B times probability of B. And from what we also just erased, you can also see that that this is the same thing as this. It's just saying that basically when you want to find A and B, you want to first see that this first part is telling you about this first part is telling you about basically B, and then this part is telling you about A. So this first part is telling you B given that A happened, and then this is the probability that A happened. So this is more like focusing on the probability of B, that is conditioned on A happening, but it's very much the probability of B times the probability of A. And then similarly, this is just the probability of B, or probability of A given B, multiplied by the probability of B. So this thing is just saying the probability A happened, given that B occurred, A will happen given that B happened, multiplied by the probability of B, so you have your A and your B. So these are just Bayes' rule in action, but I just want to show you that this is sort of how we can extend it, so I can figure out what's the probability Yangshi will be happy given that I just fed him. Or I could go the opposite way and then also ask, what's the probability that I'm going to feed him given that he's happy? And then I can collect data and numbers, but I just wanted to explain and motivate Bayes' theorem this way with you guys. So now I'm going to be feeding Yangshi. Let's see the probability that he'll be happy. You know, I've got this cute little cat toy here, cat treat for him. Aww. Hi, little guy. So I fed him these cute cat treats that he really likes. You like them, huh, boy? So we can now see what is the probability that he's happy given that I fed him. That's the probability of A given B in this example. Yeah, still not too happy. Hi, guy. He is much happier. Hi, guy. Hi, little guy. Aww, he's a sleepy little guy.
He's always grumpy. I think I smothered him too much. But he's always alert when it comes to food. He always loves to eat. Oh, you so cute guy. Hi, you guy. You happy? You happy? Yep, cats love to eat. I'd say he's happy. You tell me, what do you think the probability that he's happy, given that I just fed him is? What do you think it is? And by the way, please subscribe to our channel. It'll make Yangshi and me very happy. And he's happy. So, if you like this, please subscribe to our channel as well. It'll make Yangshi and me very happy. So thank you for watching, and please let us know if you have any questions at all. I am Saniya Khullar, and I hope that you enjoyed or you learned from this example of Bayes' theorem. And I'll be curious, what do you think the probability that, he's happy given that he's fed is? You think he's happy? I'm fairly new to having cats, so I may not recognize all the signs, but I still keep trying. Thank you for watching this. Lots and lots of love from Saniya, Yangshi, and this cute little orange one on top.